Alright, ASChem, here's a little video going through some of these questions for you guys for your big celebration. Now note, it is approximately 5:14 p.m. on a Friday, so I'll try to go through at least one of each of these types for you guys. I'm not going to be able to go through all of it because otherwise would not make it home until late, and would like to get dinner eventually. So but yeah, hopefully at least going through some of these will help you guys out. If you need further instructions, though, do note that we have all the videos from the past as well. So, you know, if you're like, I need more stoichiometry practice, you're in luck. Unit 7, I made like a bunch of different videos for that, right? More than an hour's worth of videos. Same thing with Unit 5, organic chemistry. So again, if you need more help, please do take a look at those videos, though I will try to go through as much of this as I can for you guys. And so, without saying anything more, let's go through it. So first off, we had Unit 5 bonding. Now with bonding, the first thing that we started talking about was the 3 different types of compounds that we have: ionic, metallic, and covalent. Now, I don't need you guys to remember the properties or anything, but I do need for you guys to remember and know how to determine between something being ionic, something being metallic, and something being covalent. And so how do we know if something is ionic, metallic, or covalent? Well, ionic is going to be something that is a metal and a non-metal. Covalent is going to be something that is a non-metal and a non-metal. Look at the plus there. And then lastly, metallic is if you have a metal and a metal. Okay, so that's how you're going to determine between these. And so, you know, grab a periodic table. Remember the staircase, that's also going to be up during the celebration, right? So you can make the staircase remembering that everything on the left is going to be a metal, everything on the right is a non-metal. And so here, NaCl, right? Na is a metal, Cl is a non-metal, so this clearly falls under category of ionic. CH4, C, and then remember H is the only one that's on the left side, but is a non-metal, non-metal, non-metal. This is going to be covalent. Okay. And so H2O, HO, both non-metals, so it's going to be covalent. Then Mg, Fe, both of these are metals, so it's going to be metallic. So that's how you do these types of problems. Then going on to number 2, and the reason why it's really important that you know this is because formulas depend upon what you have. Remember, so now that you know how to do ionic and covalent, there's no real rules for metallic, note, but when you have ionic or covalent, right, ionics don't have prefixes, okay, in their names. And so you determine the formula from the charges. Okay, so you have to determine charges to get the formula. Versus for covalence, you're going to have prefixes. And so you can use that. You can use the prefixes to get the formula. Okay, and so here, strontium chloride, strontium is Sr, chloride is Cl, and so we have a metal, non-metal, and so therefore we're ionic, and so we have to determine the formula based on the charges. Well, what's going to be the charge of Sr? Where it has 2 valence electrons, and so it's going to have a +2 charge, and then Cl has 7, so it's going to gain 1 electron, and it's going to have a -1 charge. And so remember, there was one of 2 ways that you could do that. Actually, there was 3 ways you could do it, but one of the ways is to say, okay, well, Sr, the +2, we need 2 Cl -1s, right, to be a -2 here to cancel out the +2. And so based on that, you can be like, well, so therefore that's SrCl2. That's one way of doing it. The other way of doing it is you could say, okay, well, Sr is +1, Cl is -1, and so we're just going to take those charges, cross them, and take the positives. And so it's going to be Sr1, Cl2. Of course, we never really put the 1, and so the clean way of writing it is SrCl2, which is just the same thing, right? And so that's how you would determine that formula. Going on to B. B is copper 1 oxide. Remember, what the heck does this mean? That tells you the charge. And so here, what we have is Cu, that's copper, Cu with a +1 charge, and then we have oxide, oxygen, with an O, so that's a -2. And so we need 2 +1s to cancel out the -2, so it's going to be Cu20. And you could have done also the cross method, right? So you would have had Cu2O1, which is really just Cu2O. Okay, cool. Let me do C for you guys over here. Okay, so C, copper 2 oxide, okay? The 2 tells us again the charge, that's +2, and then O -2. Remember, right, this 2 is for the metals, and the metals are always going to be losing electrons, and so therefore it's going to be +2, right? Sometimes kids are like, how do you know if it's +2 or -2? But it's like, it's the first thing, right? The cation, the metal, it's always going to be positive, right? So Cu +2, O -2, actually these are just good already as it is, right? It's just Cu and O, right? Because +2 and -2 just cancel if you have one of each. So we're good there. And then silicon dioxide, we see silicon and oxygen. So that's a non-metal, that's a non-metal, and we can see actually here the prefix, right? And so we see that with the prefix, that's what's telling us how many we have. And so silicon is Si, oxide is oxygen, and so Si. Di is 2, so remember, you do have to have your prefixes memorized, right? Mono, di, tri, tetra, etc. And so do have those prefixes memorized, but yeah, so that's the answers for these. Now let's just do a couple more. Phosphorus, mononitride, and so phosphorus is just P. Mono means 1, and so and then nitride is nitrogen, and so so you have just Pn. Yeah, and so that's it. Again, because P and N are both nonmetals, so we can just go based off the prefixes. Now do note, nitride is different than nitrite. Okay, please be careful. Or nitrite, nitrate, those are different than nitride. The ides are always the endings for when you have anions, right? That's just normal, right? With all these, it's ide. Except for once we get to phosphate, right? Where that's the polyatomic. So please also have your polyatomics memorized. You need to be solid on those. We've done these many times. So hopefully you're feeling good about those. But if not, just please review them. All right, okay. Let's just do this one then, just to go over one with polyatomics. So ammonium, remember ammonium is a polyatomic, and so ammonium is NH4 plus 1. And phosphate is PO4 minus 3. This entire thing is plus 1. This entire thing is minus 3. So we need 3 of these plus 1s to cancel out the -3. And so kind of the clean formula will be NH4, 3, PO4. There you go. And so remember, having this 3 says that all of the things in the parentheses will have 3 of them. So very nice. All right, so that's how you get the formula given the name. Now how can you get the name given the formula? So here we have SiBr6. We see here it's Si and Br. These are nonmetals, and so the name is going to just be so they're nonmetals, so it's covalent, so we need prefixes, right? So we need prefixes here. So silicon and then bromide. Now, how many silicons are there? It's 1, so you might be tempted to use mono, but remember, we actually don't put the mono in front of the first element, okay? For the second element, we could, but we never put it for the first. Remember carbon dioxide, that's CO2. We don't say monocarbon dioxide, we just say carbon dioxide. And so no mono, silicon, there's 6 is hexa, so silicon, hexabromide. Now, going on to number 2, or B, we see Mg and O, that's ionic. And so now you see why I brought up this question again, right? It's important to be able to do this because here, covalent versus ionic, MgO, right, that's going to be based on charges. And so Mg is going to be a +2, O is a -2. And so actually, that's just 1-to-1. We're good there. So you don't need to do anything. Actually, I'm sorry, as I'm doing this, I'm realizing you don't even need to do that, right? Because actually, for ionics, it's actually super simple. All you have to do is write magnesium oxide. It wouldn't even matter. So for example, this is MgO, right? But even if it was like Mg2O, it still would have been magnesium oxide, right? No matter what, for ionics, we don't have prefixes, so it's always just going to be the first element, its name, and then the second element with an ide ending. That's it. So ionic is actually super easy. With covalent, yeah, you have to bust out the prefixes, but for ionic, actually, super easy. Cool. Okay, let's do N2O4, and I think we're good. N and O are nonmetals, is covalent, so therefore we need prefixes. Nitrogen here, and then the second one is oxygen, so we're going to do oxide. That's dinitrogen for 2, and then 4 is tetra. So dinitrogen tetraoxide, or you could have also write tetroxide. That also would have been okay. Cool. Okay, so then drawing Lewis diagrams. Remember, the thing with Lewis diagrams is a lot of them are easy because all you have to do is just draw it out and say, okay, how many bonds do they need to form? So for example, F. Right, it's like, okay, you draw it out. It's like, okay. The problem is that one lone, or that one unbonded electron. And so that unbonded electron, we need to form one bond. Now, the good thing is we have another fluorine, which needs the same thing. And so all you have to do is that. Right? And so kind of the clean version is drawing it like this. Now note, that's the easy way, right? Basically, you kind of draw it out and you're able to figure out like, oh, this only needs one bond, this needs one bond. It's easy, we can do it well. There are some that require you to go through the 5-step method. I'm not gonna go in depth on the 5-step method here. Go back to the Unit 5 video if you need to. But yeah, there is that 5-step method in case it doesn't work out easily, okay? You have that to fall back on. So again, try to do it easily at first. If it doesn't, remember your 5-step method, okay? I know it's annoying to go back and do it, right? But that's why it's final. And that's also why I say it's chem. For example, regular chem doesn't have to do that. But for you guys, right, we do want to know those more complex ones. And so, yeah, so that's F2, O2, kind of a similar story, right? It's like, okay, we have 2 unbonded, so we need to form 2 bonds. And so, therefore, we're going to put these 2 guys next to each other. We're going to form 2 bonds. Now remember, right, basically what we're saying is oxygen has 4 for itself, and it's sharing 4. And so, right, it has 8. Same thing here, right? Has 4 for itself, and then it's sharing these 4, so it has 8, right? We want to fulfill the octet for all of them except for H, HE, Li, BE, and B. Those ones are okay with 2. But cool, okay. N2, right? It's going to want to form 3 bonds, because it has 5. It's going to want to form 3 bonds, so it's going to look like this, where it had 2 on its own, and it shared 3. So it shared these 3 in order to get 3, basically, in this share. Cool, okay, so I'm gonna keep going. I'm gonna try to do a hard one for you guys where it's like we need to go through the 5 steps. And SF6 and PCl5 are kind of hard. SO2 is also hard. Okay, let's go through SF6 because SF6 is one of the ones that, you know, when you do it, it's like, okay, we have S and F. And so, you know, if you think about the 5-step method, one of the steps, the first step really, is you have to think through, okay, well, how many valence electrons do I have total? So it's like, okay, we have 6 fluorines, each of which have 7, so that's 42, plus the 6 from sulfur, so that's 48. Okay, second step is we got to figure out, okay, who's in the center, and it's always going to be the less electronegative one that's in the center, as well as the one that can form more bonds. Fluorine can only form 1, sulfur can form 2. It also is less electronegative. If you take a look at the sheet, right, which will be given on the celebration, and so it's like, okay, sulfur is going to go in the middle. It's kind of weaker of sorts, and so it's going to go in the middle, and then we're going to arrange the fluorines around it. Okay, kind of, we call this like the petal model for drawing molecules. It's pretty effective in general, thinking of it like the center and then its petals. Cool, okay, and so now we have 48. What you're going to do, right, the third step is you're going to form single bonds first. Okay, so we're going to put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we just used 12, and so, you know, we did do the third step. So now I'm going to kind of slash it now to 42. We went for 48, sorry, not 48, 42. We used 12, so we should go down to 36, right? And then the fourth step is you're going to give electrons to make the atoms happy, starting with the ones on the outside, and then giving whatever's left over to the center. Okay, and so let's see, we have 36, so I'm going to give 1, 2, 3, 4, 5, 6. Fluorine now has 6 plus 2, 8. It's happy. Okay, I just do 6, 7, 8, 9, 10, 11, 12. I'm going to do that for all these, actually. Okay, so 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30. I have 6 more, which I'm going to just give here. And sorry, that kind of blended. But so there's my 36, right? And so I just used up all 36. So now I have 0. Now the fifth step is you got to see, is everyone happy? If anyone isn't happy, you're going to form double or triple bonds with the center in order to make everyone happy. And so we look at this and we're like, okay, is everyone happy? Are the fluorines happy? Well, yeah, right? Remember, I was telling you guys 1, 2 in the center, and then we have 2, 4, 6, 2, 4, 6, 8. And so yeah, every fluorine, right, looks like this, if you think about it. And so they're all happy, right? All the fluorines are happy. Now, we ask ourselves, is the sulfur happy? We're like, okay, sulfur is going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Or sorry, not 14, right? I think I double counted. But still 12, that's a lot. That's more than 8, right? So you might be saying like, no, that can't be right. But the thing is, you can't do anything else. Right? The fluorines aren't going to want to form more bonds. Fluorine only wants to form 1, and fluorine is pushy. It has an electronegativity value of 3.98. You're not going to get fluorine to share more, right? It's very electronegative. It's very aggressive. It's not going to want to share more. And so you're kind of stuck with this. You have to have this. This is what SF6 looks like. If you look it up, that's what SF6 looks like. Now you might say again, sulfur is not happy. And I will tell you that this is one of the ones that breaks the octet rule. Right? So remember, you can break the octet rule. You just have to ask yourself, like, is there anything else I can do? And the thing is, no, right? I mean, we did everything right? Like, we put the less electronegative one in the center. Yeah, we did. We put the rest on the edges of it. We didn't break any electron, right? We had 48, we used all 48. We don't have more than we should have had, we don't have less. This just is the correct structure. It should break the octet rule, right? And so that is correct, right? So remember, or I guess it's really exception to the octet rule, right? So exceptions happen when you can't do anything, right? Remember, these rules are just things that I give you that tell us about 90% of the case situations, but there are situations where nature is just more complex than that, right? We want to put nature in a box, but that is not how nature works. We are trying to make sense of a complex world. I apologize to you, I did not create that world. Though it would be sick if I did. But no, I'm just telling you about it, right? I'm not even telling you about it. I'm just passing the message that other people have figured out, right? And so this is how it works. Now, it is kind of cool, though, that the world that we live in is so complex, right? It would be kind of boring if it wasn't. But it is complex, and this is one of those things. There are exceptions to the octet rule. So do note that, okay? For example, N is also an exception to the octet rule, but I'll let you figure that one out. Cool. Okay, so going on, let's also do SO2. SO2 is an interesting one because it also breaks it doesn't break the octet. We have to go through the 5-step process because here's the thing. We look at SO2 and we're like, okay, sulfur wants to form 2 bonds, and then these oxygen, then we're going to put sulfur in the center because it's less electronegative, right? You might say they both want to form 2 bonds, but sulfur is less electronegative. So we're going to put it in the center. And then, so oxygen wants to form 2 bonds. But the problem you can see here is if oxygen wants to form 2 bonds, and then sulfur, and this oxygen also wants to form 2 bonds. There's like, sulfur is like, no, dude, I don't even have that many electrons. I guess I could take these and put it here, but the problem is if it does it like that, right? So I took those 2 electrons, I'm gonna put them here, right? So sulfur had 6 and it still has 6, but now it got 7, 8, 9, 10. That's not great. Now you might say, but there's an exception to octet rule, but I'll tell you actually, no, you could do something else, right? And so it's not an exception to the octet rule. So let's go through the 5-step method and you'll see like, nah, we could do this in a different way. You don't have to make it an exception to the octet rule. So let's see. So the first step, right, is to figure out how many valence electrons we have in total. How many valence electrons do we have? We have 6 plus 6 plus 6, right? So we have 18 valence electrons, and then 2, we're going to figure out what goes in the center, and it is indeed sulfur in the center because it is the less electronegative. Now we're going to form initial single bonds because you have to have at least single bonds here, and so we're going to have 14, and then we're going to give electrons to the others to make everyone happy. And so we have 1, 2, now we're going to have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we actually just used up all. Nice, good job. We had 14, we just used them all up. Cool. And then the 5th step is form double and triple bonds. Oh, and actually, no, I'm sorry. I've messed up. Right, someone hopefully was saying it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I had 14. I had 2 more, so I have to put on the sulfur. Okay, remember the remainders go on to sulfur. or onto the center atom. Cool. Okay, so now I've used all 14. Apologies for that. But so now in step 5, you form double and triple bonds in order to make everyone happy, if necessary. And so let's see, is everyone happy? Well, the oxygen has 1, 2, 3, 4, 5, 6, 7, 8, so it's happy. And then this one also has 1, 2, 3, 4, 5, 6, 7, 8, so it's also happy. But the sulfur has 1, 2, 3, 4, 5, 6 only, right? 1, 2, 3, 4, 5, 6. Yeah, it only has 6. And so it's not happy. So we got to form double and triple bonds. And so what we could do is we could move these two here, right? The 2 electrons here, I'm just going to put them here. We're going to share them, okay? And so again, I didn't destroy electrons, I didn't add electrons, I literally just took these 2 and I put them here to share instead. And so now sulfur has 1, 2, 3, 4, 5, 6, 7, 8. And this oxygen still has 1, 2, 3, 4, 5, 6, 7, 8. And so this is a good structure for SO2. Now you might be saying, why couldn't we take the electrons from here? And I would tell you, actually, yeah, we can. And so what you can do is you can also draw it like this. Both are valid. And actually, both are so valid that both are happening in real life. SO2 is oscillating between these 2 structures. And so actually, an even more accurate way of doing it is to say that it's like this, where sulfur has a bond with oxygen, then kind of a half bond. So it's like 1.5. And so what we say here, right, as I've been kind of mentioning to you guys a bit, this is what we call resonance, right? And so it's resonating. SO2 is resonating between these 2 structures. The real best picture for it is this hybrid of the 2. And so anyways, that's resonance. Remember, that's just a bonus thing that you can do. My point is I'll take either of these answers. And actually, if you say there's resonance, I'll give you a bonus point. So anyways, resonance, 5-step method, right? That's going to be the hardest drawings that you have to do, but do note that's how you do it. Cool. Okay. Shape, the biggest thing is, please, you have to have and draw your chart. Now let me grab that chart for you guys. Right, you need to draw this into your study guide. And so, no note, I didn't go over these guys for you guys, so you don't really need these ones, but you do need all these. And so here, you're going to first draw your molecule, and then try to determine what its shape is. And so BF3 here is going to be B, F, this, and yeah, put the electrons. Now, this also, again, is actually an exception to the octet rule. B only has 6, but is happy with that because that's all you can do. Anyways, that's not what I'm trying to do here. Okay, if you're confused, please feel free to look it up more. But this is what BF3 looks like. So BF3 looks like this, and so the question is, what's the shape? And remember, when we're looking at shape, we only care about the central atom, what's happening around the central atom. We don't care what's happening with the fluorines, we care about what's happening around B. And around B, we can see there's 1, 2, 3 electron domains, 3 bonds. And so we're like, okay, there's 3 things around it, none of which are lone pairs, so we fall into this situation. So it's trigonal planar. A student was asking me today, is there going to be trigonal planar? And I told her, no, there is going to be trigonal planar though. And so it's okay, you don't need to actually know how to pronounce these things, but trigonal planar, that's how you say it. And so it's going to be a trigonal planar. What was it? Trigonal planar. Is that what she said? I don't know. Whatever. Trigonal planar. That's how you say it. And so yeah, just literally draw your things out. And again, it's about what's around the central atom. Okay, just match up, right? This is, yeah, B, and then the 3 Fs, right? So we have a trigonal planar. Okay, so that's how you do those. Going on to number 6, give the formula of the following molecule. We're finally here, organic chemistry. I love organic. There will definitely be organic on the celebration. Now, I know sometimes you guys get confused with it, but it's really not hard. Let me actually just show you guys a couple things. Basically, this is the idea behind organic. This is how we learned it, okay? What's this? All right, hopefully at home you're saying this is 1, 2, 3, 4. This is meth, prop, bute. This is butane, right? This is butane. And so I would say to you, yes, good job. Now, well, actually, I don't want to, I guess I'm going to have to actually. Okay, yeah, that's butane. Cool, okay. So now I'm going to draw another butane for you. And then I'm just going to do this. And I ask you, what is this? And I hope you say, well, you added a double bond, so now it's not butane anymore, it's butene. And I would say yes. Now what if I did the same thing, but I did this? And again, hopefully you say, oh, yeah, it's the same thing, basically. You just put a triple bond, so it's butane. Butane, ene, ein. A, E, Y, which is the order of those vowels in the alphabet anyways, right? And so that actually makes a lot of sense. Cool, okay. So, you know, hydrocarbons, right, or these are carbons here. But yeah, you know, butane, butene, butine, that makes sense. Okay, now what if I took butane and I instead added an OH? And you would say, well, yeah, that's still bute, but it's butanol, because it's an alcohol, okay? Alcohol, butanol, okay, cool. That becomes butanol. And I'd say, yeah, very nice, okay. What if I did, instead of doing that, what if I did this? And you would say, yeah, we still have 4 carbons, but you added on a carboxylic acid, Cu, right? Cu. And so you would say, okay, that's not going to just be butane anymore. It's going to be butanoic acid, right? The carboxylic acids, anoic acids. So this is going to be butanoic acid. And I would say, yeah, very nice. And then I would say, okay, what if instead I did this? And you would say, well, we still have 1, 2, 3, 4 carbons. So it's butane, but it's like in a circle. It's enclosed. And so it's cyclobutane. Right? And so what we're seeing is, right, it's very similar. So long as you remember meth, eth, prop, bute, right? It's like, okay, I can actually figure out a lot of these, right? Just remembering a couple of things that single bond is A, double bond is ene, triple bond is ein. Anytime you add an alcohol, we put ol. Anytime you add a carboxylic acid, a Cu group at the end, it's anoic acid. And then anytime you make it a circle, it's cyclo at the beginning. So, right, it's just small variations. There's a couple other things, but like if you can just go through that, right, you genuinely know most of the organic chemistry stuff we talked about in class. So anyways, don't freak out about it, right? Genuinely, just go through your study guide, the old organic chemistry study guide I gave you guys, some of your Union 5 stuff. But let's go through these 2 for you guys, and hopefully that helps you guys out. So here we have A, 1, 2, right? And so that is methane. But the thing is actually this isn't asking for name, it's asking for formula. Okay, so what we have to do here is we have to say, okay, so each of those ends are a carbon. Now remember, carbon needs to have 4 bonds. We have 1, 2, 3, 4, and each of those bonds are going to be hydrogen, right? Those hidden bonds that there wasn't anything, those are going to be hydrogen, okay? So that's how you do that. So it's C2, 1, 2, 3, 4, 5, 6 hydrogens. Nice. Similar here, right? We have carbon, so always draw on the carbons first, and then make sure there's 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. Nice. Cool. C3. 1, 2, 3, 4, 5, 6, 7, 8. C3, H8. Nice. Okay. So that's how you do those. Now, note that this is butane, right? As we were mentioning, that's C4H10. Now, note that this is also actually C4H10, as is this. These are what we call isomers of one another. You don't have to know that, but that is true. So if you were saying, wait, I got the same answer, that's true. Yeah, I mean, because we still have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. These are just, again, isomers of one another. These have the same formula, but they have different structures. And they're actually very different as a result. They have very different properties. But I'm going to leave that for your future chemistry courses to tell you about. But okay, continuing on, right? What we see here is we have all these carbons, and then we're going to form 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4. And then we're going to fill in the hydrogens. Nice. 1, 2. Okay, so C4. 1, 2, 3, 4, 5, 6, 7, 8. C4, H8. Nice. Okay. So that's how you do that one. And that's how you do those in general. Okay. Yeah, now I did want to kind of comment on this guy, right? In a perfect world, I would have found a picture that looks like this. Right, like this is, I think, would have been easier for you guys. But note, okay, anytime you have a nitrogen, or anytime you have something and it's like, okay, they just attached a hydrogen onto it like that. Basically, that hydrogen's supposed to be bonded. They just didn't bond it. We don't put hydrogens on the carbons, right? That's assumed. But for other things, we would put the nitrogen, or we would put the hydrogens on it to tell us that there is a hydrogen bond there. And so that's what this really looks like. But yeah, again, you could have actually just figured this out though by putting carbons on. And then just literally doing the same thing as before, and then just having the N and the H here in the formula at the end. I just wanted to break that down though, because 2 people asked me about that, and I'm like, yeah, just that N, that H is bonded to the N. Okay, that's what it's looking like. Unfortunately, this was the best picture I could find. Most of the times chemists are taking a lot of shortcuts. Like, this is kind of annoying to draw, and so the pictures I found online were like this. Now note, this is actually methamphetamine, meth, and so that's why I also put it on there. It's a interesting molecule. I know all you guys all the time ask me, are we gonna break bad? No, we're not gonna break bad. This is close we're gonna get. But yeah, methamphetamine. This is sucrose. So a lot of you guys are gonna see that next year. So, you know, just trying to put some interesting molecules on there for you guys. But yeah, same ideas. I know these are kind of annoying to put all those carbons in, but you can do it. Cool. Okay. So going on to number 7, right? Fill out the following table. We have butane here, and it has meth, eth, prop, but. It has 4 carbons. So then we're going to make sure that we have all the bonds. So that's all of them have 4 now. And we're going to put on the hydrogens. Nice. So that's its Lewis structure. Its line drawing is just meth, pro, but. 1, 2, 3, 4. Nice. And then the formula, as we've done before, is C4H10. You could count it up there, but yeah, C4H10. Cool. Okay. Continuing on. Let's see. Let's maybe do hexanol. Hexanol, right? Hex is telling us, hey, that's 6 carbons. And so it's like, okay, 1, 2, 4, 5, 6. Okay, cool. And then 1, 2, 3, 4, 5, 6. Now note on this last one, since it's not specified, you can put on any one you want, but we're just going to put the OH, that OH group on the end, and then all of these H's here. Cool, and there you go. And so then line drawing 1, 2, 3, 4, 5, 6. You can add the OH, nice. And then formula C6H13, OH, I believe. Let's see, 1, 2, 3, 4, 5, 6. 6 times 2 is 12, plus 1 is 13, and then OH, yep. Nice, C6H13OH. Cool. Propanoic acid, I do want you guys to remember to be careful, right? Prop means meth, eth, prop, 3 carbons. And so it's like, okay, 1, 2, 3. Now remember though that that 3rd carbon is gonna be where the COH is, right? Propanoic is telling us there are 3 carbons. And so that 3rd carbon, right? You can only have 3 carbons here, right? It's not like we're adding, it's like, oh, we have a propane group and then we're adding on the carboxylic acid. No. It's like we have OOH added onto, really, that's C. And so that's what this would look like. Okay, so do be careful. You can only have for propanoic acid 3 carbons, okay, total. And so the problem is sometimes you'll write the formula like this, where it's like C3, 1, 2, 3, 4, 5, 6, H6O2. And sometimes it'll be written like C2, H5, right? C2H5, COOH, and kids will get upset. They'll say like, but 1, 2, that's only eth. And I'll say, yeah, I know, it's kind of annoying, but it's like 2 carbons here, and then we add that 3rd carbon there. I know, kind of annoying, so be careful. It's kind of tricky. Okay. Methyl cyclohexane, or also this could be, you could also write it as, actually no, that's really the only way we would write it. Sorry, I was thinking of something else. Because you could also write, for example, cyclohexyl chloride or chlorocyclohexane, but that doesn't work for these ones. But anyways, so cyclohexane, hexane is 6 carbons, but it's a cycle, and so I'm just going to do the line drawing here. So 1, 2, 3, 4, 5, 6 carbons, and then we're going to add on a methyl group. It's not telling us where, so we're going to add it on anywhere. That's a methyl, right? And so we're just going to add it like that. Now, it actually might be helpful to see it like this. Sorry. Because you might be saying, that's just a line. And I'll say, yeah, it is a line, but, right, basically. And actually, let me take off one of these, right? So here's all the hydrogens, hydrogen, hydrogen. Nice, okay. And then we're adding on this methyl group, right, which is basically, right, this is a methyl group, right? And so, yeah, we're adding it on here. Now, what does that look like? Well, we're just going to put the carbon, and then we don't put any of the hydrogens, right? So it's like there's a carbon there, but none of the hydrogens, right? And so that's how to think about that. Cool. Okay. So methyl cyclohexane. All right. On this one, I actually gave you guys the line drawing, and I want you to figure out the name, right? The name of this, based on the line drawing, is going to be like, okay, well, we have 1, 2, 3, 4, 5 meth prop bute, and then pent. Okay, so that's a pentane, and we added on a chlorine, and so we could call it chloropentane, or the other thing is you could call it pentyl chloride, which is, I think, how I've been doing it. Now, do note that the chlorine, actually, we can be a little bit more specific, because on the third carbon is where we're putting the chlorine, right? And so we could call it 3-chloropentane or 3-pentyl chloride. Either way, but do note, right, that you do need that, because otherwise, right, like that's different than if we were to put the chlorine here, right, on the second carbon, right? Like those are two different things. Now I know you might be saying it's like, no, they're not, they're the same, but they're not. They are different, actually, and they have different properties as a result. Okay, so I know you might be saying it's like, why do we care? But it actually does really matter, as you'll see later. There's a reason why chemists are trying to, you know, in their nomenclature, they call this 3-chloropentane versus 2-chloropentane. There's a reason for that. There is actually a difference there. Not a huge one, but it does matter. Cool. Okay. Now note, some students also might be saying, like, why do we call it chloro? And that's just how it works. Meaning, like, for example, this would be, if we had a fluorine, we would have called it 3-fluoropentane. This is chloro. And take a wild guess what you think bromine is going to become. Right, that's going to be bromo. Right, and so the halides, halogens, right, we're going to just turn them into O's. So fluoro, chloro, bromo, right? Don't get overwhelmed. Don't be like, what does oxygen? Oxygen doesn't work that way, okay? It's just a halides. Fluoro, chloro, bro. I guess we do iodo, but I never really use iodine. I don't really know if anyone does. So yeah, fluoro, chloro, bromo. Cool. Okay, that's all you need to know. 3-chloropentane. Cool. All right, so moving on to number 8. It's almost already 6 p.m. Well, we'll do as many as we can. If anyone, I guess no one's gonna watch this in time because I'm gonna upload it later. But you know, if you watch this later, please bring food outside of J5. Though I'm not there, but in Memorial, I suppose, at some level. But yeah, going on to number 8. What IMF is present? This again really comes back to a lot of this, right? There's a reason why this is so important. If you can't tell the difference between ionic, covalent, and metallics, but especially ionic and covalent, you're going to be in trouble, because the IMF that's present really depends on if we have ionic or covalent. If you have something that's ionic, you're going to have an ion-ion. IMF, right? Versus if you have something that's covalent, there's actually 3 possibilities for you. You could have, well, the first thing is, do you have covalent, or do you have polar covalent, or do you have non-polar covalent? If you have non-polar covalent, then what you're going to have is the induced, or the London dispersion / LDF IMF, right? And so it ends there. But if you have polar, you have to figure out, do I have, is it just like a normal polar, or is it polar as a result of H with phone? Remember the phone? I had someone try to call me on my phone, right? With fluorine, oxygen, or nitrogen. If you have H bonded to, and maybe I'll do it like that. If you have H bonded to fluorine, oxygen, or nitrogen, then you're going to have what we call a hydrogen bond IMF. It's an extremely high dipole. It's like a super dipole. And so H with phone is going to be, hydrogen bond IMF. Now note, it's not actually a bond, it's an IMF, which is why that's such a stupid name. But I apologize, we don't really have a choice about that, right? But yeah, so that's, or if it's normal polar, right? It's not one of the special ones, H with FON, right? It's just, you know, we have a polar covalent bond without this special situation. If it's just normal polar, it's going to be dipole. Okay. And so remember, ion-ion is the strongest, hydrogen bond is the second strongest, dipole is the third, and then induced / LDF is the fourth. Okay, and so what IMF is present here, you got to figure out, okay, is it ionic or covalent? If it's ionic, it's easy. If it's covalent, you got to go through a bunch of other steps. So here we're like, okay, SR is metal, Cl is non-metal, and so this is ionic, so it must be ion-ion. Nice. Then H2O, right? Draw it out because H and O are non-metal, so this is covalent, so we got to go through this whole thing. We got to figure out is it polar or non-polar, and remember how to get polar or non-polar. It depends on, is there a dipole? Is there a big difference in electronegativity? O and H, there is a 1.24 difference. That is a huge difference. Now, remember the thing is, do the poles cancel? And the answer here is no, right? We both have them going left and right, right? So like the left and rights cancel, but they're both going up towards oxygen. Oxygen is pulling up. And so no, there's an overall net force up. And so it is indeed polar. Right now, is hydrogen bonded to F, O, or N? And the answer is yeah, hydrogen is bonded to O, right? So we actually have a super dipole. It's super polar, it's a hydrogen bond IMF. And so this is very polar, it's hydrogen bond. That's the IMF that's present. If we didn't have H at all, right, and H not bonded to F, O, or N, we would have just had normal polar, it would have been dipole, but that's not the situation we're in here. And so HF here, again, right, H and F, this is a non-metal, so it is covalent, and so I have to draw it out. It's like, okay, cool, drawing it out. Is there a big difference? There is. That's a 1.78 difference. And so big difference, there is a pull, no one's canceling. There is a net pull, therefore it is polar. Is it H with F, O, or N? Yes, it is. It's H with F, and so it's a hydrogen bond. So therefore, very strong IMF. Cool, okay. Let's do CH4. This is CH4, it's like this. It is covalent. Now C and H, there's only a 0.35 difference actually, so there aren't any pulls, so there's no net pull either, and so therefore it's just non-polar, so therefore it's induced / LDF. Cool, and then let's just do this last one, CH3, Cl. Again, we know there's no pulls here, but there is actually a big difference here between C and Cl. It's greater than 0.5, and so there is a pull here. Now, therefore we're polar. Is it H with F, O, or N? No, it's just normal polar. So therefore it's dipole. Now technically also all of this, for example, is just induced or LDF, and this part is the only part that has that strong where it's like, okay, this is partial positive, this is partial negative, and so therefore the stickiness between this and another carbon with chlorine, right? Remember, that's what an IMF is ultimately. Remember, I had that one practice problem a long time ago where it was like, okay, this is partial positive, so the strength of attraction, the IMF, is here, and so there's a super strong attraction here, but then there's no attraction basically here with these guys or these guys. So you could, if you really wanted to, A+, you could say like everything that's going on, but I don't need you to do that, right? The IMF that's present though is you need to say that there is dipole. If you didn't include like induced or LDF, that's totally okay. But you know, a strong force of attraction like this, the fact that this has, you know, the partial positive, partial negative as a result of a big electronegativity difference that would cause big IMFs with another CH3Cl molecule. You do want to mention that, right? You do need to have dipole in there. So cool, okay. So for example, FC2H5OH, right? You don't have to mention the induced LDF, that is the majority of it, but that OH hydrogen bond, right? You really do want to mention that. You want to analyze that. Now, if you have a huge molecule like C5H11OH, and it's like, okay, most of this is just induced LDF. I'm like, yeah, that's pretty accurate, actually. You can just say induced LDF, and I wouldn't expect you to talk about the hydrogen bond. But here, where it's only a couple things, like, please do talk about that hydrogen bond. It is important. But cool. Okay, so that's how you do IMFs. Continuing on to unit 6. Let's try to go through this quick. How do you do molar mass? Remember, molar mass is simply about the masses here, right? It's about the average atomic mass. Now, back then we did it in AMU, but now it's in units of grams per mole because it's not exactly the same, right? There's similar ideas, but they're not exactly the same. Anyways, though, right? So the molar mass of hydrogen is 1, carbon is 12, right? If you want, put some more sig figs, but I'm trying to go fast. So 1, 12, nitrogen is 14, right? And so, for example, H2O is going to be H is 1, oxygen is 16. So total is 1 plus 16 plus 1. Oxygen weighs 18 grams per mole, approximately. Okay, so that's how you do those. Now, once we get to something like this, where it's like a name, yeah, you do have to translate silicon dioxide into its proper formula, so that then you can say like, okay, Si weighs 28, oxygen weighs 16, but there's 2 of them, so that is 32. 32 plus 28 is equal to 60 grams per mole, right? And so that's how you do molar mass. It's really not hard. All you have to do is take a look at the numbers, the masses, and then just add them up. Let me actually do one more. That would be especially hard for you guys. Sodium phosphate is probably, no, that's actually not hard either. These ones require you to know your polyatomic. Surprise, surprise. Well, actually, not even surprise. I can't even say surprise. Not surprise. You need to know your polyatomics, right? Please, y'all, know your polyatomics. I sent an announcement on it as well. Please remember your polyatomics. I know it's annoying, y'all, but how was your age, though? I memorized even more of them, right? Because you had to. I tried to just have the ones that were most essential, but we can't get around it. Chemistry has polyatomics involved. So many of the compounds I have in the lab have polyatomics. I couldn't not teach it to you, right? That, like, first of all, it'd be chemistry malpractice because your future teachers, professors, biology teachers would be like, dude, how do you not know about polyatomics? But also, like, I couldn't do a lot of labs because I wouldn't have the material. We couldn't use the material because you would have said, what's carbonate, right? So we needed to learn it. Please know it, okay? So for example, potassium nitrate is going to be KNO3, right? Now, the reason why I was like, none of these are very hard is because what if you had, and this is not true, okay? But, oh, let me change this, right? What if instead you had MgNO3 right? Remember, with that, it's like, okay, we have Mg and then 2 NO3s, okay? Like, that's basically the idea here. So you have to take the mass of NO3, right, which is going to be 14 plus 16 plus 16 plus 16, right? And then do all that twice, okay? So 14 plus 16 plus 16 plus 16. And then the mass of Mg, which is 24.3, right? So you have to add this and this and this, okay? All of these have to be added. You can't just do, like, you need to, you know, distribute out that 2, okay? So you need to have 2 nitrogens, 6 oxygens total, okay? Anyways, that's how you do those. Okay, mole conversion problems. Remember, 2 things you really need to have on your sheet is you need to have the definition of the mole. The mole is 6.022 times 10 to the 23rd molecules of a substance are in 1 mole of that substance, okay? And so you need to have that. And remember, what we're doing ultimately here, whenever we're doing these type of problems, is you are doing, what do you call it? You are doing dimensional analysis, where you start off with what you have, you multiply by fact in fraction form to get what you want. And so here, for example, if we have 25 grams of water, well, and it's asking us to get to moles, well, we have something with grams of H2O on bottom, moles of H2O on top. Those are the units, which will cancel to get us what we want at the end. But the question is, what numbers go here? It's like, okay, well, how many grams of H2O are in a mole of H2O? That's the molar mass, right, which we just reviewed here. So it's 18 grams of H2O in 1 mole. 25 divided by 18 is going to get you, what's the way you do it? 25 times 1 divided by 18. 25 times 1 divided by 18 is going to be 1.4 moles of H2O, right? Okay, so remember, take what you have, what you're given, times it by a fact This is a fact. It's called the molar mass. Multiply by a fact in fraction form to get what you want. Okay. Cool. So how many grams are in 2.5 moles of CO2? 2.5 moles of CO2. How do we get 2 grams of CO2? Well, you just have moles of CO2 on bottom, grams of CO2 on top. 44 is the molar mass. 44 grams of CO2 are in a mole of CO2. So you just do 2.5 times 44 and you get 110 grams of CO2. Okay, let's do a little bit of a harder one for you guys. How many molecules of sulfuric acid, H2SO4, are in 5 grams of sulfuric acid? Well, okay, we have 5 grams of H2SO4. We're trying to get to molecules. This is a two-stepper where we have to first go from grams of H2SO4 to moles of H2SO4, right? So 1 mole of H2SO4 is how many grams? Well, let's see, 2 plus SO4, which is 60 plus 16 plus 32, 98. I think, let me just do that one more time. 32 plus 16 plus 16 plus 16 plus 16 plus 2. Yeah, that's 98. Cool, okay. So then we get moles. Now to get to molecules, you have to do the other step, which is to multiply by the definition of the mole. So 1 mole of H2SO4, right, is equal to 6.022 times 10 to the 23rd molecules of H2SO4. So moles, you get to molecules at the end, right? And so we have the right unit. So all we have to do is do 5 times 1, which is just itself, times 6.022 times 10 to the 23rd. So we get that, and then we're going to divide by 98. And so we'll get 3.07 times 10 to the 22nd molecules. Very nice, right? And so remember, 2 things here, the molar mass, the definition of the mole, right? Multiply by those things in fraction form to get what you want. Now you could have broken this up, right, where you kind of did an intermediate where you were like, okay, 5 divided by 98, that's 0.05 moles of H2SO4, right? And then 1 mole is 6.022 times 10 to the 23rd molecule, so 0.05 times 6.022 times 10 to the 23rd will be 3.07 times 10 to the 22. You know, you could have done it in 2 steps. I like to do it all in one like that, but again, you could have done it either way. Cool, okay, so percent composition is really easy. I'm not gonna go through that, unless I stay here till 9. Percent composition here, the hint is where the H atoms are not drawn, so draw them to determine how much they are and their weight, right? So here, just remember these carbons, okay? And so here we have carbon, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 4, 1, 2, 3, 4, yeah, 1, 2, 3, 4, cool, okay, so I'm gonna add these hydrogens, right, and so then we have, oh, geez, we still have that carbon, and we have 2 more hydrogens, cool, okay, so then, right, once you get the formula here, right, you'll get C, 1, 2, 3, 4, 5, 6, 7, 8, C8, and then how many hydrogens? 1, 2, 3, 4, 5, 6, 7, 10, H10, and oh, sorry, I didn't add this carbon, did I? 1, 2, 3, 4, 5, 6, 7, 8, no, I did, okay. And then we're gonna have 1, 2, 3 oxygens. So C8, H10, O3. Okay, so once you get the formula, then it's just like this one, right? Where all you have to do, right, is take the mass of this, right? So percent comp is always going to be equal to mass of total over mass of element, right? And so, for example, here, the mass of the hydrogens, right, the percent hydrogen is going to be 10 grams. Really, actually, it's AMU, 10 AMU over whatever the total mass of this is. What? That's 8 times 12 plus 10 plus 16. Sorry, plus 48, right? So 10 over 154, right? Now, I will say I'm doing this pretty quickly. I might be wrong, so forgive me if I am, right? But that's the idea. Percent hydrogen, for example, is going to be 10 over 154, so 6.49. Yes, sorry. That should be times 100, right? So 6.5%. Nice, okay. So then we go on to number 4. What is the empirical formula for the compound, right? So now this time, right, we have percent, you want to get the formula. So here we had formula, we wanted to get percent. This time we have percent, we want to get the formula. And so the way to do this, remember, is to go from percent to grams to moles. And so, for example, let me do B for you guys. 79.8% copper and 20.2% sulfur. What you want to do is you want to turn those percents into grams, right? By assuming a 100-gram sample. So you get now 79.8 grams of copper and 20.2 grams of sulfur. So now that we have 79.8 grams of copper and 20.2 grams of sulfur, then what you want to do is you want to convert both of those into moles using the molar mass. And so, well, for copper, 79.8 divided by 63.5 is going to be 1.26. And then sulfur, 20.2 divided by 32.06, you're going to get 0.63 moles of sulfur. Now, for those of you who are good at math, you'll see already that this is basically, there's 2 times more moles of copper from moles of sulfur, right? So it's in a 2-to-1 ratio. But for those of you who aren't as good at math, here's an algorithmic way to do it. Basically, once you have this, right, the formula is basically 1.26 coppers for every 0.63 sulfurs. But of course, no one writes things like that, right? We want them in whole numbers. And so what we want to do is you're going to take both of them and divide them by the smaller of the two. So 0.63 is the smaller of the two. So 0.63 divided by itself is just going to be 1. And then 1.26 divided by 0.63 is 2. And so that's what I meant when I said it was 2-to-1, right? Really, don't want to write that. You want to write copper 2, sulfur 1, but we don't ever put the 1, right? And so that's how you do empirical formula from the percent compositions, right? Just take your percentages, turn them into grams, and then turn them into whole numbers. Cool. Okay. Well, the good news is we're about an hour in, and we've gone through at least a couple, but we still got a lot more. So let me at least get through Unit 6, and let me figure out what I need to do. Okay, so number 5 is a simple little vocabulary one, right? Remember the video, the song, right? That nice old man? A solution is a type of mixture. How did it go again? That the solute is the thing that gets dissolved. The solution is the solvent is the thing that does it dissolve. Anyways, go watch that song. Hopefully that'll put the vocab in your heads, because you do need to know those vocab words, especially for biology. It'll be important, right? But basically, the solute is always the thing that gets dissolved, and the solvent is the thing that does the dissolving. Okay. So solute, solvent, and then a homogeneous mixture, right, is a solution. How did it go? A solution is a type of mixture. Mixture that is homogeneous. Yeah, there you go. Right, see, if you remember the song, actually, you could eventually figure out all these vocab words. It'll come back to you. So anyways, I'll spare you guys from my off-tune singing. That's also because I don't have time. But also, even if I did have time, I wouldn't sing this. But go listen to the song. It'll get it into your heads. But so then the other thing that you need to do is not just be able to describe solutions, but also to be able to do problems with them, right? And really, these are pretty simple if you just remember molarity is equal to moles over liters. And so here, right, molarity is equal to moles over liters. And so we have 1.0 moles. We want to make 0.1 liters. What is molarity? So molarity here is going to be, 1 mole over 0.10 liters. And so you do 1 divided by 0.10. That reset, 1 divided by 0.1. It's going to be 10 molarity. That's the unit of molarity. It's capital M for molarity. You could have also done moles over liters. That's the other unit for molarity. Cool. Okay, so that's 10M. Now, B gives you it in grams, and you got to turn it into moles. 1 gram of potassium is going to be equal to 1 divided by 39.1, because that's the molar mass. It's going to be 0.03. So that's 0.03 moles. And so then it becomes the same problem, right? It's like, okay, well, 0.03 moles over 0.10 liters is going to be equal to 0.03 divided by 0.1. That is 0.3 moles over liters. Nice. Or, right, 0.3 capital M. Technically, it's M of potassium fluoride, right? For each of these, but cool. Okay. Now do note that, for example, I think for G, this is a dilution problem. So M1V1 is equal to M2V2, right? Where this is the before and this is the after. So if we have 340 milliliters or 0.34 liters, right, of 0.5 molarity, right? That's what we had. Will the concentration be, so what is M2 if we add 560 milliliters? Okay, so we do 340 plus 560. So that's going to be 0.90 liters, right? And then you just solve for M2. Okay, so just remember, before, after, M1V1 is equal to M2V2. Cool. Okay, will it dissolve? Why or why not? Remember, those are all based upon if something's charged or not. If you have a charged compound, it will dissolve in water, right? Because water is charged, because it's polar, right? Polar, there's plus, minus, partial positive, partial negative, right? H2O is polar, it's charged, and it will dissolve charged things like salt, right? Salt, NaCl, Na is +1, Cl is -1, right? It's ionic, and therefore it's charged, and therefore it will dissolve, okay? So remember, things that are ionic or things that are polar covalent will dissolve in water. Anything that's non-polar, like this, right? This is covalent, but it's non-polar, and so therefore it's non-polar covalent. Therefore, it's not charged. Therefore, it will not dissolve, right? And so do you see how important it is and why I'm starting off, right? I'm including this thing from Unit 5 of the ionic covalent, and metallic doesn't really matter as much, to be completely honest with you. I mean, it's important, but it's like not as important. Like, it's important that you know it for future science class. But moving on forward in this class, ionic and covalent, right? That's a hugely important thing that you need to be able to just like have like that, right? To know like the metals are here, the non-metals are here, right? You need to be able to do that because it determines so much. For example, these dissolving rules as well. And then also polar, non-polar. You also need to be able to be really good at that. So practice that a lot. A lot of the other questions really rely upon that. Cool. Okay, so number 8, will a precipitate form? If yes, indicate what the precipitate will be and explain why it will precipitate. What this comes down to is it's all about what we form at the end, right? And so we don't even really need to worry about the beginning. It's about your products. And the rule here is, or at least for our class, the rule here is if you have a +2 and -2 or higher in the charges of your compounds, right, then you will get a precipitate, okay? But, what that means basically is that you are gonna have a compound where they are so attracted to one another, the anion and the cation are so attracted to one another that water isn't gonna be able to pull them apart, and therefore they will continue to be a solid that's not dissolved, and therefore it's gonna precipitate out. Anyways, again, take a look at my slides if you want a more in-depth review of that. But basically, so we look here and it's like, okay, Ca, what charge is it gonna be? It's gonna be +2. And SO4, we know because we memorized our poly atomics, is -2. And so +2, -2, right? That is the situation. And so this is gonna precipitate out. K is +1, NO3 is -1, so actually this won't. But yeah, this precipitate will form, CaSO4. Ca has +2. SO4 is -2. So therefore, a precipitate will form. Since H2O can't dissolve it. There's strong Coulombic attraction there. All right, nice. All right, so that gets us at least to Unit 7. Now let me lie down for a second and then figure out if I'm gonna go eat dinner or if I'm gonna try to finish this up. But cool, all right, at least we got to Unit 7.